Hi, in previous videos, we understood how ML systems are deployed and architected. In this video, I'll show you why most ML models fail after deployment, even if accuracy was high during training. These are not coding mistakes, these are real world system problems. So let's understand it. Machine learning models often fail in production environment because the condition they were trained under different significantly from real world scenarios. Unlike controlled development settings, production system face dynamic data streams, evolving user behavior and unpredictable external factors. For example, a credit scoring model trained on historical data may underperform when economic conditions shift, leading to inaccurate prediction. Another critical point is that models are part of larger system and failure often stem from integration issues rather than algorithm flow. So by end of this video, you will understand why ML failures are system failures, not model failures. The most common production issues in ML systems, how builders think about failure before deployment, and why monitoring matters more than accuracy. So architected versus deployed ML systems. Let's understand it. There is a stark difference between how machine learning systems are architected during development and how they operate once deployed. In development, assumptions about data stability, feature availability, and infrastructure reliability often hold truth. However, in productions, these assumptions break down due to real-time data variability, system load, and operational constraints. So in production, ML models does not fail suddenly. They fail silently. Silent failures in production. Let's understand it. So one of the most critical insights for ML practitioner is that model often fail silently in production. Unlike traditional software bugs, which typically produce visible error, ML failure manifest as degraded performance without explicit signals. This can lead to significant business impact before detection. For example, a recommendation engine may gradually lose relevance as user preferences evolve, yet continue to operate without triggering alarms. So let's understand the specific failure modes. Failure 1, data drift and its impact. So, data drift occur when the statistical priorities of input data changes over time, causing models to perform poorly. The data your model see in production is not the same as training data. So some of the real world examples are loan model trained on 2021 data. Economy changes in 2024. User behavior shifts. Model accuracy drops silently. So the builder explanation is the model is not wrong. The world changes. So second failure is training and serving skew. Training and serving skew arises when the data pre-processing step during training differ from those applied in production. For example, cleaned training CSV, production raw API input, missing values handled differently. So the builder insight is same model plus different pre-processing equals to different predictions. So failure 3, feedback loop problems. Feedback loop problems occur when model prediction influence future data, creating self-reinforcing pattern that can twist outcomes. For example, recommendation system only shows what model already prefer. model becomes biased over time. So the key line is the model start learning from its own decision. Now, failure 4, lack of monitoring. Monitoring is often neglected after deployment, leaving teams blind to performance degrade. Effective monitoring involves tracking input data quality, output prediction, and system health metrics. For example, drift detection tools can alert teams when feature distributed change, while performance dashboard can highlight drop in accuracy or user engagement. So, implementing alerting mechanism ensure timely intervention before failures escalates. So, failure 5, business reality mismatch. A model's technical success does not guarantee business impact. Business reality mismatch occurs when models deliver accurate prediction but fail to align with operational workflow or strategic goals. For example, a churn prediction model may identify at risk customer accurately, but if business lacks a timely retention strategy, the insights remain unused. This disconnect highlights the importance of integrating ML solution into broader decision making processes. So, before deployment, ask what can change, what can break, how will I know, and who will respond. These are some of the questions that should be asked before deployment. So, understanding common ML production failure is essential for transitioning from experimental model to reliable systems. If you understand these failures, you are already thinking like a production ML engineer, not just a model builder. In the next video, we will talk about how teams design system to handle these failures. So, see you in next video. Thank you.